Hi everyone, welcome back. We can continue this chapter and learn about how businesses measure their quality. Well, for the businesses to measure their quality, they need to have an understanding about their process capability. In other words, is the process capable of meeting the quality standards and providing acceptable quality on a consistent basis? Process capability ratio, C sub P, is the most common measure that the manufacturers use to measure their quality. It measures whether or not a process is potentially capable of meeting certain quality standards. Well, in calculating this process capability ratio, we have the tolerance limit, and then we divide that by 6 sigma. Um, as you know, the manufacturers usually specify a certain tolerance limit for different measures related to their product, such as the weight of that product or the height, width, length of that product, mostly physical attributes. For example, if you look at a pack of bottled water, if you exactly take a look at them, you will notice that not all of them are filled up to the same level. So there is some very little differences in the level of water that exist in every bottle within that pack. And of course, the manufacturers will set that tolerance. It will be based on the type of product they are producing, the industry that they are performing in, right? And as a result, we have an upper and a lower tolerance limit. So when we take the difference and divide that by 6 times the standard deviation, we can get the process capability ratio. So this sigma is the standard deviation of the process. In other words, how much spread we have in that specific measure related to the product that is being produced with that process. So let's take a look at it. Let's think about it, because you might wonder why we use 6 sigma in the denominator. Well, that's because of the properties in the normal distribution. In a normal distribution with a mean of mu and the standard deviation of sigma, approximately 99.7% of the observations will fall within 3 standard deviation above the mean and below the mean. So that's one of the property which we can see in every normal distribution, regardless of the mu or regardless of the value for the mu and standard deviation. So if you look at this range of 6 sigma, which is mu minus 3 standard deviation all the way to mu plus 3 standard deviation, so it's like the area under the curve within this range will be approximately 99.7%. It's a helpful property as it helps us do the interpretation with respect to whether or not the process is capable of meeting the quality standards 99.7% of the time. Well, let's discuss the interpretations according to the value we get for the process capability ratio. So when you calculate the process capability ratio, so you divide the tolerance limit by 6 sigma, if it's at least 1, if it's equal to 1 or greater than 1, that means the process is capable of meeting the tolerance limits 99.7% of the time. In other words, the process is capable to make defect-free products 99.7% of the time. And that's the case where your tolerance limit is, at least 6 sigma. So you're falling within this range or wider range. So it would end up getting a value of at least 1. On the other hand, if your ratio results into a value which is less than 1, So you will probably fall within this range. So your basically ratio has a value of less than 1. That means the process is not capable of meeting the tolerance limits 99.7% of the time. Let's take a look at an example. Big Bob's Axles has a customer that requires axles within a diameter of 25 centimeter plus or minus 0.02 centimeter. The customer has stated that Big Bob must meet these requirements 99.7% of the time to keep the business. They are able to make the axles with a process mean of exactly 25 centimeter, which we see here, and the standard deviation of 0.005 centimeter. So what is the process capability ratio? In other words, is Big Bob capable of meeting the customer needs? Okay, so first of all, you need to calculate the upper and lower tolerance limit. Let me go out of the slideshow and start writing here. So the upper tolerance limit is 25 centimeter plus 0.02, which will be 25.02. And the lower tolerance limit is 25 centimeters minus 0.02, which is 24.98. Okay, so as you calculate the upper and lower tolerance limit, you can take the difference as the top part of your ratio. So that's what we have here, 25.02 minus 24.98. And then divide that by 6 times the standard deviation. The standard deviation was given in the question. So this is our standard deviation of 0.005. Right? So we will have 0.04 over 0.03, that the end result will be 1.33. According to what we learned with respect to the interpretation, we have a ratio which is larger than 1. So that means Big Bob process is more than capable of meeting the tolerance limit 99.7% of the time. In other words, it can make defect-free axles 99.7% of the time. So it's capable to meet the customer's needs. Well, that brings us to the idea of Six Sigma quality. It takes us, steps further. The organizations that have achieved Six Sigma quality have really superior quality levels. And achieving the Six Sigma quality is very difficult in practice. It requires a lot of effort and a lot of improvement. So if the business is able to reduce the variability of the process to the point where the process capability ratio is greater than or equal to 2, that's where they achieve the Six Sigma quality. In other words, they have worked on improvement of their processes over time to the point where only 2 out of 1 billion observations will fall outside the tolerance limits when this process is working. Right? So that's huge. Only 2 out of 1 billion observations will fall outside the tolerance limit. That means the process is really working in its superior way. And that's a big deal. Okay. So Six Sigma quality builds up on the idea of the process capability ratio and shows us how the businesses can improve their processes to the point where the process capability ratio can be a value greater than or equal to 2. Now we can talk about continuous improvement. We talked about it in the previous lecture. So continuous improvement is the philosophy that even small incremental improvements can add up to significant process improvement over time. It offers a set of tools for applying logical thinking and also statistics concepts to um, identify the issues and make improvements. Well, we want to learn about those tools. One of the tools is root cause analysis using the cause and effect diagrams. Basically, when there is a problem or issue, it's important for the cross-functional teams to get together, discuss that issue, brainstorm about possible causes of that issue, and through using some structured analysis, they can narrow down all those possible issues into only a few major causes. So when they have identified the root cause of the problems, it's going to be easier for them to focus only on a few major root causes and hopefully resolve and fix the problem. So one of the tools for the root cause analysis is the cause and effect diagram. It's also known as the fishbone or Ishikawa diagram because Ishikawa is one of the pioneers who has made significant contributions in the field of quality management. As part of that, he introduced this cause and effect diagram. Well, in the cause and effect diagram, we have the main branch. It's like the main bone for the fish, which shows the effect, which shows the problem. For example, our problem is that we have late deliveries, or the problem is the lost order, or high defect levels, okay? And then we start brainstorm and identify all possible causes. Some of the causes could be related to the methods, where we have, poor designs, we have poor processes and procedures. Some of them could be related to the manpower. We don't have the people with the right skills. Some of them related to the measurement systems. Some of them could be categorized under machines, or some of them are related to the materials. So we can categorize all those possible causes into 5 categories. We call them 5 M's: methods, manpower, measurements, machines, and materials. Let's talk about an example here. Let's say at a pump manufacturer, the problem is that they have variations in the pump shaft dimensions. So we put that on the main branch here. Then they can think about the causes. One cause could be related to the methods. They have complex process. They have complex product designs. So I would add a branch to it. And what is the cause for this cause itself? So maybe the reason was that the designers didn't talk to the manufacturers. There was this lack of communication between those. Okay, and then we ask ourselves again, what is the cause? Why is that happening? So we would make another sub-branch, right? Why the designers are not talking to the manufacturing, okay? And what is that? What is the cause of that one? So we break down the causes into other sub-causes. Or it could be due to the manpower. There's poor training for the workers. Why there is poor training for those workers? Well, maybe one cause it would be due to not enough budget. Okay, and then we can further break that down into other sub-causes. Or another cause could be that the workers don't have a really good motivation to do their work properly. So low motivation. Why do they have low motivation? Maybe because they are paid, they are not really paid well. Okay. With respect to the machines, it could be the cause related to the machines. So we have infrequent maintenance for the machines. Or the other reason could be we have old machines, old equipment, and they can't really hold up to those tolerances. It could be related to the materials. So we have poor machine, fluid, poor so material. Why do we have poor material? Because probably we didn't spend much time in designing an effective contract. So we have ineffective contracts. Why do we have ineffective purchases? Again, think about that and what is the cause for that? So you can see that we are thinking about all possible causes and breaking down those causes into other sub-causes. We will do that until we can get to the root causes. So when we get to the root causes, those are the ones that we have to concentrate on and hopefully resolve the problems in our business. Okay, so that's about the cause and effect diagram. I brought up an example to make it more clear to you how it works. Scatter plot is another continuous improvement tool. If the problem is that we have high defect rates and we are suspicious whether the overtime hours is making higher defect rates, we go ahead and make a scatter plot that shows the relationship between these two variables. And we can see that as the overtime increases, the defect rates also increase. Probably that's because the workers are more tired, working during overtime hours, and that makes this problem. Okay. But with the scatter plot, we can only see the impact of one variable at a time. Maybe it's better to make a check sheet where we can list all possible causes. At a grocery store like Whole Foods, we have had this unexpected delays at the checkout counter, and then we started listing all possible causes and how many times each happened. Well, out of 391 total delays, 142 times that was due to the price check that was taking time for the clerk. 14 times was related to the register being out of money. 12 times related to the customers for getting the item and then going back in order to grab their item out of the shelves, coming again to check out. So there are different possible causes. And with this check sheet, we can see which cause is the major one. So here, the major cause is the price check. So instead of complaining about the customer, why they forget their items, it's better to really focus on creating a more comprehensive and accurate price list, and also training the clerk on basically learning how to do those price checks and do the process of checkout for the customers. With the Pareto chart, we can translate the check sheet into a chart. So we can see which cause had the highest frequency. At a restaurant, let's say we have 65 number of times the total orders that are prepared incorrectly, and we start to investigate the causes. Well, out of that, 22 times it was due to the waitress that took the incorrect order information. 19 times it was due to the cook who heard the order incorrectly. 12 times related to the food that is not cooked properly, and 8 times the food really doesn't match the menu. Okay, and other reasons, other causes for 5 number of times. So here the major issue is with the waitress and probably the cook. So these are the most important causes that the restaurant really needs to focus on to fix this mistake, and hopefully they can prepare the orders more properly after resolving the issue. Statistical quality control is another approach for continuous improvement. As we want to monitor and control the processes in the manufacturing setting, we can use the control chart, and it helps the company track changes in their key measures over time. Those measures are such as weight, length, height, width, or the temperature for that item, or any other physical attribute related to the item being produced. Well, in the manufacturing setting, it's not that they make 1,000 items every day and they inspect all those 1,000 items, because that's going to be time consuming and costly. So instead, they take a smaller sample and measure to evaluate their quality of that sample. So we want to basically introduce 2 continuous variable measures, including the sample average and range. Okay, these are what you have learned before in the basic statistics. To refresh your mind, the sample average X bar, it takes the average of the values within a sample, and the range R, it's the easiest or the simplest type of measure for the standard deviation. The range takes the gap between the largest value in the sample and the smallest value in the sample. Let's take a look at this example. A quality team at Milburn Textiles want to set up control charts to monitor the dyeing process. So the temperature shouldn't be too high or too low, because if it's too high, the fabric will be too dark. Also, if the temperature is too low, it will be problematic because streaks can develop. Well, what they do, they take samples over 10 days to provide the base for their control charts, and hopefully this base will be used to control their process in the future days. As you see, in every day, they take a sample of, let's say, 5. So their observation, the sample size is 5. And then these are the temperature for those items. They record the average of those temperatures. So the average of this temperature in this sample is 139.2. And then the range is the difference between the largest temperature and the lowest temperature. So the largest temperature in this sample is 144, and the lowest one is 136. The difference is 8. Again, on the second day, they take a sample of 5. So they calculate the average of that, which is 140. They calculate their range. So the highest value is 139. Minus the lowest value, the highest value is 143 minus the lowest value of 138. So the difference is 5, and that would be R. In the same way, they calculate X bar and R for the other days up to day 10. Also, they take the average of all these averages. It's called X bar bar, X double bar. which is 139.8. They also take the average of ranges, which is R bar. The average of R's is a 5.3. So these two values are used in order to create a base for the control charts, and they will use that control chart for monitoring their process in future days, starting from day 11. For example, in day 11, they again start as collect a sample. They record the sample average. They also record the range for that sample. They perform the same for the other future days. They record their average, X bar, and also their range. And now they can make their control chart. So in making the control chart, let's focus on, first of all, this chart. So this is a chart that they develop using X bar, the value that we figured out in the previous table. So this X bar would be the center of this control chart. And then according to that, they would set an upper control limit and lower control limit. So in defining the upper and lower control limit, they would use specific parameters that are based on the sample size and based on the industry. So that's above the scope of this course. So we don't want to go into the details of that. But generally, they would use the parameters to develop the upper and lower control limits. So when they have that chart, they can start controlling and monitoring the process for the future days. For example, for day 11, it shows that X bar falls within this control limit. The same for day 12, it will fall within the control limit. So these are the points related to the X bars for day 11 and 12. For day 13, it looks like that X bar is 144, which is outside the control limit. So it's getting out of control, and they have to investigate and see why that is happening. Okay, work on that. And when they work on that, they can bring the process back to control. As we see during days 14, 15, and 16, the values are within the control limit and it looks good. In the similar way, we can have a control chart for their range. So this is built using the range value, using the average R that we figured in the previous table, 5.3. So that would be the center of this control chart. And then they will also calculate the upper and lower control limit using some fine-tuned parameters, and start looking at the process, whether it's in control or not. On days 11 and 12, those R values are within the range, but at day 13, similar to the one we see above, at day 13, it's getting out of control. It's outside of the control limit. So they will work on that. They will bring the process in control, and we see that the process starts to be within control for the future days of 14, 15, and 16. Okay, in this lecture, we learned about process capability. We learned about the quality measure of process capability ratio. Also, we talked about several different continuous improvement tools. So please make sure to let me know if you have any questions. Thank you for watching and have a great one.